Funding for this program is provided by Annenberg CPB to advance excellent teaching.
Isaac Newton's law of universal gravitation explains why all bodies near the surface of the Earth fall with the same constant acceleration. Newton's law explains why the apple, but not the moon, falls from the sky.
50 years after it happened, Isaac Newton told someone that his great discovery had something to do with seeing an apple fall from a tree. And that story became part of our folklore. We like it because it's so ordinary. A lot of apples have fallen from a lot of trees. And it also reminds us of another story about another apple, the one from the tree of knowledge that led to our leaving the Garden of Eden. Well, Newton's apple, whether it was real or not, made it possible for us to escape from the Earth itself. Of course, Newton's great accomplishment was not in showing that gravity makes apples fall. You polished that for me. Of course, everyone always knew that. His great accomplishment was in showing precisely and mathematically that the same laws that explain why the apple falls also explain why the moon stays in the sky. That explanation was the key to the universe as it was then understood. The details are difficult and important, and we'll get to them, but not today. Today, I want to explain to you how he first reasoned the problem through and how he proved he was right. It all came down to a 20th of an inch. You might say it was the first 20th of an inch of our voyage to the moon.
On the way to the moon, young Isaac Newton might have taken this path. 3 centuries later, a trio undertakes a journey that surpasses the voyages of Marco Polo, Magellan, Columbus, Drake, perhaps every earthly explorer since the first primitive step into the unknown. These men are bound for the moon. Their destiny has already been determined by engineers and scientists, by technicians and visionaries, researchers and test pilots, by the best laid plans, and all the right stuff. But everyone here from the ground up stands atop the shoulders of one man, Isaac Newton. If an apple really played a role in Newton's law of gravity, it must have done so on the fields of Lincolnshire. Of course, history is written with many such ifs. For example, if Newton hadn't returned to his family farm at Woolsthorpe Manor, he might not have discovered anything. Anything, that is, beyond the infamous Black Plague of London. In 1665 and 1666, its daily toll was darkened with figures almost too grim to recount, because the plague was almost too horrible to imagine. The infections were epidemic, malignant, contagious nearly beyond human control, a disease transmitted from rats to fleas, and from fleas to every walk of British life. The plague could destroy 9 out of 10 human beings. Cambridge, the university community about 50 miles from London, was not spared such dreaded visitations. There, the Black Death could have claimed Isaac Newton. But in 1665, he headed for the hills of Lincolnshire. And in that bucolic setting, Isaac Newton lived to solve some great mysteries of the universe. To see the world as it really is, Newton had to approach it along a revolutionary path. To reach a totally new understanding of the universe, it would take a worldview deeper and broader than the familiar vistas of the English countryside. He was only 22 years old, and for someone with only an undergraduate degree to his credit, indeed for a young fellow who'd never traveled farther afield than Cambridge, the universe was an enormous challenge. Intellectually, a revolution was already afoot, and its seeds had been planted by Nicholas Copernicus. Professor of mathematics, doctor of medicine, scholar of canon law in the Roman Catholic Church, Nicholas Copernicus single-handedly laid the foundation for modern astronomy. At the turn of the 16th century, after having studied at the University of Krakow in his native Poland, Copernicus lectured in Rome. In 1512, he moved to the city of Frauenburg, East Prussia, where he practiced medicine and served as canon of the Cathedral of Frauenburg. There, sometime around 1530, he wrote the treatise that changed not only the world, but the entire universe. He wisely dedicated his work, The Revolution of Heavenly Orbs, to Pope Paul III, and he prudently withheld publication until he lay near death in 1543. But he'd made his point, the Copernican system, and no power on earth could suppress it forever. Based on ancient astronomical data, the Copernican system was in some ways only a minor improvement over the Ptolemaic system. Both viewpoints were, to a large extent, based on the philosophy of Aristotle, particularly the ancient Greek mandate that all heavenly motions were perfect circles. And therefore, like countless astronomers before him, Copernicus used epicycles to explain the apparent deviations from uniform circular motion. Nonetheless, Copernicus placed the sun at the center of the solar system and put all the other planets, including the Earth, in orbit around it. And thus Nicholas Copernicus did the spade work. Some viewed it as dirty work for Galileo Galilei. In the Renaissance, the Copernican system was a clear and present danger, but only in theoretical terms. Even if astronomers had wanted to oppose the Aristotelian views of the Church, none could prove the planets orbited the sun. And besides, none tried. None, that is, until Galileo turned his intellect to the task. With Copernicus in the back of his mind and the latest technology in hand, Galileo came to grips with some earth-shaking concepts of his own. With inclined planes and the ability to imagine the world in a vacuum, he perceived the law of falling bodies. All objects fall with the same constant acceleration. At the same time, imagining a world without friction. These experiments led Galileo to another profound idea, the law of inertia. On a smooth horizontal plane, a rolling ball would never come to rest. Like all objects on Earth, it would retain its motion unless something altered its course. With his acceptance of the Copernican system and his mathematical insights about motion, Galileo explained how things work on Earth. It took 3 more laws to explain how things work above and beyond the Earth. These 3 laws were the contributions of Johannes Kepler. Kepler's first law gave the orbits of the planets a new non-circular shape and put the sun a little off the center. He realized that a planet is sometimes closer to the sun and sometimes farther away. According to Kepler's second law, the closer the planet got to the sun, the faster it moved. And the farther away a planet got from the sun, the slower it moved. His third law said that the larger a planet's orbit, the longer it took to go around. Kepler's 3 laws describe the heavens with unprecedented precision. In a field investigated by Copernicus, Galileo, and Kepler, Newton began to unearth the still-buried secrets of the universe, not only of the heavens, but those which remained hidden within his own planet. Giants before Isaac Newton had explained the how of heaven and earth. Now it was his turn to rise and to explain the why. Before Newton, no one knew why all bodies fall at the same rate, nor why the moon orbits the earth, nor why the earth orbits the sun in a precise path at a precise rate. Before Newton, probably nobody even imagined these phenomena were related. So it fell upon young Isaac Newton to create a new science to unite heaven and earth. But once again, if an apple ever played a role here, its role was secondary. Newton's accomplishment was no flash of insight in the orchard, inspired by chance. He worked furiously for 18 months, and yet 20 years would pass before the fruits of his labor would be published, and nearly 300 years would pass before the final seconds of a countdown. Launched from Newton's shoulders, men could finally free themselves of Earth by casting off the chains of gravity. The force of gravity is no small barrier. Its strength can be appreciated by viewing the tremendous force it takes to break free. But when humans are launched into outer space, toward the mysterious regions of the moon, a mere appreciation of gravity isn't enough. It's necessary to know how it really works. Newton assumed that every 2 bits of matter in the universe attract each other. The force of attraction is proportional to each of their masses. The force weakens inversely as the square of the distance between the 2 bodies. This law can be represented as a vector equation with a constant of proportionality called g. G is the same for any 2 bodies in the universe.
I told Michael you guys are up there, and he said, who's driving?
That's a good question. I think Isaac Newton's doing most of the driving right now.
Since the force of gravity on the moon is less than it is on Earth, everything on the moon weighs less than it does back home. Things fall more slowly, even though there's almost no atmosphere on the moon. But still, all bodies, even a hammer and a feather, fall at the same rate. Why? Newton's law. It says there's a force between any 2 particles of mass anywhere in the universe. Therefore, every particle of mass in the astronaut is attracted by every particle of mass in the moon. What's the net effect of all these forces added together? Each body attracts the other as though all of its mass were concentrated at its center of mass. The force the Earth's gravity exerts on an apple, for example, is minus g times the mass of the apple times the mass of the Earth, divided by the square of the distance from the center of the apple to the center of the Earth. For all practical purposes, that distance is the radius of the Earth. But force is also mass times acceleration. So when made equal, the mass of the apple cancels from the equation, leaving an acceleration that doesn't depend on the mass of the apple. Gravity has the same effect on any object near the surface of the Earth. Half a century before Newton, Galileo discovered that all bodies fall with the same constant acceleration. With his law of gravity, Isaac Newton explained this strange phenomenon. The acceleration of any falling body on the Earth is little g. It's equal to the universal gravitational constant, big G, times the mass of the Earth divided by the square of the radius of the Earth. That combination gives an acceleration of 32 feet, or just under 10 meters, per second per second. On the Moon, the same force is at work, but the acceleration is different. It still depends on the universal gravitational constant, but now the mass is the mass of the Moon, and the distance is the radius of the Moon. The net result is that the acceleration of a falling body on the Moon is 1/6 of what it is on Earth. While necessarily interested in falling bodies, Newton sought to explain something else about gravity. If apples fall to the Earth, why doesn't the Moon? Could it be that the same law applies? Newton's argument was to imagine someone casting a projectile horizontally, firing a cannon, for example, from somewhere high above the Earth's surface. From Galileo's discovery, Newton already knew that a body dropped from 16 feet above the Earth's surface reaches the ground in 1 second. The distance a cannonball travels depends on its velocity. If the projectile leaves the barrel at 30 feet per second, it travels 30 feet before it hits the ground, 1 second later. But Newton realized that if the projectile were fired fast enough, it would take more than 1 second to reach the ground. The Earth would curve away before the cannonball reached it. In fact, he could imagine a cannonball moving so fast it would never strike the ground. It would just keep falling forever, while the Earth forever curved away beneath it. In other words, it would be in orbit.
All right, stand by one, we'll get you that earthquake. See, up here we don't know where over is. One up is as good as another. That really is water, though, I'll show you.
Zero G, or weightlessness, isn't really the absence of gravity. Astronauts orbit the Moon, held there by gravity just as surely as gravity holds the Moon in orbit, or pulls an apple to Earth. The objects floating around in the cabin are in free fall, just as the spacecraft itself is. Together, they will continue to fall in their orbit around the Moon, just like Newton's cannonball in orbit around the Earth. Isaac Newton knew that the Moon, just like the cannonball, keeps falling, falling through eternity, never reaching the Earth. The Moon falls toward the Earth with an acceleration of g times the mass of the Earth, divided by the square of the distance to the center of the Earth. The formula is the same as the one for the apple or any other body on Earth, except that now the distance isn't the radius of the Earth. In this case, it's the much larger distance from the Earth to the Moon. The rate at which the Moon falls is smaller than the rate at which the apple falls. It's equal to the radius of the Earth divided by the distance to the Moon squared. That ratio has been known since antiquity. Greek mathematicians calculated the distance to the Moon as 60 times the radius of the Earth. The Moon should fall more slowly than the apple by a factor of 60 squared, or 3,600. Since an apple falls 16 feet in 1 second, Newton concluded that each second the Moon should fall a distance of 16 feet divided by 3,600. That distance is 1/20th of an inch. That was the prediction made by Isaac Newton's theory of gravity. The next crucial step was to compare theory to reality. In other words, the question facing Newton was, how far does the Moon actually fall every second? How could he deduce the answer from what he knew about the Moon's orbit? He knew the Moon goes around the Earth in a nearly circular orbit, and he knew it takes about 1 month to make the trip. According to the law of inertia, the Moon doesn't want to travel in a circle. It wants to fly straight off on a line that is tangent to the circle. In 1 second, it would go 40,281 inches along the line. By following the circle, the Moon is actually falling. That is to say, it's falling away from the line and toward the center of the Earth. This is the distance the Moon falls in 1 second.
By the Pythagorean theorem, Rm squared plus d squared equals the sum of Rm and Sm squared. So d squared equals 2Rm Sm plus Sm squared, a quantity so small it's safe to ignore. Given the size of Rm and d, Sm is 1/20th of an inch.
For the world at large, how enormous that 1/20th of an inch would turn out to be. That bodies would fall forever under the influence of gravity had been proved by an astounding agreement between theory and observation. The proof that 1/20th of an inch would explain, in practice as well as theory, Galileo's mysteries of falling bodies and the heavenly motions of Johannes Kepler. Yet marvelous as this secret was, another 20 years would pass before Newton would share it with the world. Nonetheless, at that moment, and with that result, that 1/20th of an inch, Newton knew that he held in his hands the key to the mechanical universe. He had taken the first step along the path that led us into space and to the Moon.
I told Michael you guys are up there, and he said, who's driving?
That's a good question. I think Isaac Newton's doing most of the driving right now.
Come in.
According to Newton's universal law of gravity, the gravitational force between any two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. Newton's law explains why all bodies fall with the same acceleration near the surface of the Earth. When combined with the law of inertia, it explains the orbit of the Moon and the motions of all heavenly bodies.
The fact that that 1/20th of an inch is the same as this one would have been enough of an accomplishment for the lifetime's work of any other scientist, but not for Isaac Newton. The list of his mathematical and scientific discoveries leaves us absolutely breathless. On the other hand, not everything he did
seems respectable to us. He dabbled in alchemy, biblical chronology, and various other arcane pursuits that, to him, seemed just as legitimate as the physics we admire so much. In 1696, he went mad, quite literally insane. Some people today think it was a case of mercury poisoning, perhaps a result of his experiments in alchemy. And there's some evidence for that from a recent chemical analysis of hairs from his head. Other people think that that was splitting hairs. Because with Newton, there wasn't much difference between mad and sane. But in any case, he recovered from his illness and became in 1703 President of the Royal Society, a position which he held for the remaining 24 years of his life. However, compared to his accomplishments, the details of his life hardly matter at all. What he gave us was not just a series of scientific discoveries, but rather a coherent view of how the universe works and why it works as it does. That view has dominated all of Western thought from Newton's time right down to our very own. Of course, he was a human being with faults and flaws, maybe even more than his share. But he was also a giant, almost unparalleled in all of history. In Don Juan, Lord Byron wrote, "When Newton saw an apple fall, he found, in that slight startle from his contemplation, a mode of proving that the earth turned round in a most natural whirl called gravitation. And this is the sole mortal who could grapple, since Adam with a fall or with an apple. Man fell with apples, and with apples rose. If this be true, for we must deem the mode in which Sir Isaac Newton could disclose, with all kinds of mechanics, and full soon steam engines will conduct him to the moon."